This is my presentation for Lab 1 Object Motion. The goal of this lab was to observe the motion of an object moving at a constant speed and direction, and compare it to a computational model based on Newton's second law, also known as the momentum principle. We used the velocity update and position update formulas to predict the object's motion, and the formulas are here shown on the right. Here is a preview of the main results. So in theory, with no outside forces, the object should move in a straight line at a constant speed. Both the observed and predicted models are showing a positive slope or velocity, but the computational model is perfectly linear while the real-life data is slightly curved. This is likely due to the friction, as it causes the object's velocity to decrease continuously until it stops, meaning that the object's velocity isn't truly constant. Part 1, the video. So for the video, we placed a meter stick on top of a flat surface, which is the table, and we pushed the object battery from the left end of the meter stick. The object moved across the table until it stopped. The system is the object or battery, which has a mass of 0.0353 kilograms, and the surroundings are the table and the hand that pushed it. Part 2, tracker. So I uploaded the video to Tracker so that I could analyze the video and extract the object's positions in corresponding times. After calibrating the axis and entering the object's mass of 0.0353 kilograms, I found an initial velocity of about 1.46 meters per second and initial position of 0.0386 meters. Part 3, Glow Script. Next, I built a simulation in GlowScript using starter code. I set the mass to 0.0353 kilograms, the initial velocity to 1.46 meters per second, and the time step of 0.033 seconds. I calculated the initial velocity of the object by using the velocity equals displacement over time. I used the first 2 points that were given to me by Tracker, and I got a velocity of 1.46 meters per second. I also adjusted the time to 1.2 seconds, and I had to apply the Newton's second law to update velocity and position using the velocity and position update formulas. The code produced a blue sphere moving to the right with constant velocity, exactly as Newton's second law predicts when net force is 0. Part 4, comparing models. So both models began with the same mass and initial velocity, and it showed a positive slope on the position time graph, which is shown by the GlowScript and Tracker graphs, or the graph that combines both of the models. Now for the differences, we can see that in GlowScript, we see that it shows a constant velocity, which is shown in the velocity time graph. On the other hand, for Tracker, the initial position started at 0.036 meters at the x component, which is due to the object being pushed right before the origin at 0 meters. The slope for Tracker is also slightly curved, and this can be explained by the friction that played into the situation. So as the object slid across the table, it slowed down until it reached a stopping point, which is non-constant velocity. Part 5, errors. So some possible sources of errors include slight misclicks when marking the points in Tracker for the object's position, a small timing offset at the start where the object was pushed right before 0 meters, so the initial position was slightly greater than 0, and of course the unavoidable friction that interrupts the ideal friction-free assumption. Part 6. The questions for this lab include, what if when I analyzed my video data Tracker and made a choice of flipping the axis from positive x to negative x? Well, if I flip the x-axis in Tracker, all the positions in the slope or velocity would simply become negative. That would mean that every point for position would be negative since the object was moving in the positive direction before its position. Well, now it will appear to decrease with time. Now for the second question, the answer is no. You can't tell how many forces add to give a net force of 0. According to Newton's second law, it only tells us the total vector sum. So saying that F net equals 0 only means that the forces add up to 0, which means that any combination of forces can add up to 0. So the experiment showed that while the computational model predicts constant velocity, the real object slowed because of friction. Ideally, with no friction, the real motion would match the model, but some possible sources of error may have affected the experiment, leading to a difference between the observed and predicted models. Thank you.